Hello, deep learners. Our guest tonight is Dr. Achin Bhowmik. Dr. Achin is a Stanford University professor. He is a former vice president and general manager of perceptual computing division at Intel Corporation. And now he is the CTO of a multi-billion-dollar medical device company, Starkey Hearing Technologies. Welcome, Dr. Achin. Take it
Thank
away.
you, Sophia. Thank you for inviting me. It's really a pleasure to come and talk to the audience and take a little bit of a dive into non-vision stuff. But I do have something to talk about vision as well. So as you mentioned at Intel, my primary focus was on computer vision, a bit on auditory part of it, because we were working on developing machine learning and artificial intelligence based on new sensors to bring about autonomous systems, flying drones or autonomous cars and all kinds of new technologies. So for the last 3 years, after I left Intel to come to the medical area, I've been focusing really hard on transforming hearing aids into multifunction devices. Today, that's what I'm going to talk about. So how we have used sensors and AI to take an old classic traditional device and we're trying to make it, like I like to say, a device that you want to have rather than a device that you need to have. So with that, let me start with a few numbers, because there's as we were talking about right before this presentation, people get surprised about how many people need help with their hearing. I myself got surprised 3.5 years ago when I got exposed to this field. So let's start with numbers. According to World Health Organization, so these numbers are a little bit older, but I'm still using them because of the reference that comes with it. Almost 500 million people about 2 years ago used to have disabling hearing loss. So disabling hearing loss is defined by I'm going to talk about these terms afterwards, but it's about 40 decibels of loss. That means in order to hear like a normal person, person with normal hearing, you got to amplify the sound that's coming into your ear by 40 decibels. So that's called disabling hearing loss, according to World Health Organization. There's 500 million people that have disabling hearing loss. By 2050, that number is expected to almost double. And as Sophia, you were talking about young people being at risk of hearing loss, and that's totally right. In fact, beyond those numbers, it's feared that about 1 billion people or more, the younger population, are at risk of developing hearing loss because we are exposing ourselves to more and more recreational sounds, music, and so this problem is getting worse. Another thing to point out, as I will discuss the neurobiology of hearing loss, you'll see that much of this is age-related. So it's called sensory neural hearing loss. As we age, the sensors of hearing degrade, and I'm going to talk about that more. So over the next decade, because of all of the advances in healthcare, medicine, and just eating healthy, more awareness about doing exercises, we're living longer. So 85-year-old is going to be the fastest growing population over the next decade. In fact, the 100 plus years is going to be second fastest. So we are, starting to live longer. That means people with hearing loss is going to be a much bigger number than what I'm showing here. So as far as the numbers go, I'm going to show just one more thing. Very few people actually use hearing aids. So even if we have more than 500 million people that have disabling hearing loss, all of 2019, there was just about 17 million hearing aids that got sold. So Starkey is one of the largest companies making hearing aids. We're the largest in the US. There are 4 large companies out of Europe as well. So between these 5 companies, there are about 99% of those devices are accounted for. So with that, so in order to make meaning of the things I'm going to talk about, I'll have a little bit of just a little bit of physics, just I'll touch sound waves, because we need to talk about that as the stimulus for hearing, just as light is the stimulus for vision. And then I'll talk about a bit of biology of hearing, the physiology of human ear and auditory cortex. And then I'll switch over to technology, talking about the products and algorithms. So let's look at sound. This chart here on the left, I'm depicting the sound pressure levels in micropascals. So that's micronewton per square meter of sound pressure levels associated with different situations, going from threshold of hearing at the bottom. So that happens to be 20 micropascals. Just ponder over that a bit. The environmental pressure at sea level is about 101.5 kilopascals, right? So 20 micropascal is considered to be barely audible levels of sound by a healthy hearing person. So that's about a billionth of the variation of the atmospheric pressure level. So healthy ear is extremely sensitive. And then on the right side of this chart, I'm showing decibels as the sound pressure level. And so decibels defined as 20 log of P over P0, P being the sound pressure level, and P0 is the reference sound pressure to the 20 micropascals. That's the threshold of hearing. So with that, let's establish the upper limit. Human ear can handle all the way up to 140 decibels. In fact, that's where you start to feel the pain. And those are dangerous levels. You do not want to be exposed to 140 decibels of sound for too long. So now if you look at this range here between about 30 decibels to about 70 decibels, so that's what we get exposed to most of the times. Conversational speech in your living room or in a business office, you might be around 65 decibels. Right now, I'm probably making about 60 to 65 decibels of sound. And then depending on how much volume you've set on your speaker, you're probably getting exposed to between 60 to 80 decibels of sound. The bad news is, as you get to a rock concert, you might be exposing yourselves to 100 decibels or higher. And in fact, when you're in a plane, we were talking about that right before I started presenting. In the plane, you might be exposing yourself to 85 to 95 decibels of sound. So it is, gets to be dangerous levels if you're exposing yourself more than a couple of hours or so. So with that, hopefully this gives you a quick idea of what I'm going to talk about later, decibels and micropascals. So here is the first marketing pitch. If you want to kind of have fun with trying to understand how loud is the environment around you, you can go and download this free app that we have made. It's freely available on both iPhone and Android phones. It's called the Soundcheck app. So you can use it to check out the noise levels around you. Even I end up checking all the time when in a plane. You hit the button and see what's the noise level. You can even check your hearing. You can do some self-testing with it, some basic self-testing, how good your hearing is. And this is a free app. So with that, now I'm going to take a quick journey into biology. It's the physiology of hearing, because we need to understand what happens when we get hearing loss, what degradation happens in our perceptual system. So human ear that I'm showing you here is an amazing organ. It's just unprecedented levels of capabilities this thing has. And so I'm going to just quickly go over it. If you want to learn more, pick up a book. I'm showing one here, the bottom right, Sensation and Perception. They're very, very good reference books that talk about human hearing, auditory cortex. So let me just go over a few key components of the human ear. Roughly, the ear organ can be divided into three sections: the outer ear, the middle ear, and the inner ear. The outer ear essentially is made of two components: the flap, the pinna, the outer ear, what you see, and we call that to be the ear, right? So obviously that's the least significant part of human ear. Even if you cut off somebody's pinna, the outer ear that is attached to a head, they will still hear fine. You lose some directionality, but you'll still hear. So this pinna and the auditory canal, that's about 3 centimeters long, we call ear canal, right? So those two are called the outer ear. So pinna essentially is you can consider it to be antenna for acoustic waves. So its job is to collect sound waves and then guide the sound pressure waves into the auditory canal. At the end of that auditory canal, you have the tympanic membrane, or the eardrum, right? And the eardrum vibrates in response to the sound pressure that impinges on it. And then that transfers the sound pressure waves or vibrations of the air molecules into three smallest bones that you have in your body. And those three bones basically are the middle ear: malleus, incus, and stapes. Those three little bones that you see there are the smallest bones in our body. So they perform the function of pre-amplifying the sound before the sound wave gets into your inner ear. Actually, I should have also mentioned the ear canal itself, because of the geometry, it also does a bit of amplification for 1.5 kilohertz to 5 kilohertz of sound waves, which is where human speech happens to be. So the ear canal actually amplifies that range of frequencies by about 3.5 decibels. And then these three middle ear bones, they work together to provide large amplification, 27 decibels of amplification. And that's because you have a large area of the eardrum, and then you got three bones that are connected in the shape of liver, around the fulcrum. So that amplifies the vibration, transferring the vibration at the small footprint of the stapes, and you get 27 decibels of mechanical amplification because of that. Okay, with that, the most of the fascinating things happen in the inner ear, and that's that green colored organ that I'm showing there. There you see the cochlea, the snail-shaped structure. So I'm going to go straight into that now. The cochlea, that's 2.5 turns. And I'm here showing the cochlea stretched out, right? Even so, you should think of this as a 2.5 turn fluid-filled snail-like structure, 2.75 turns, but I'm showing it to be stretched out. That's the organ of transduction of sound into electrochemical pulses. So in order to understand this, I'm going to take a cross-section of the cochlea, and I'm going to show that in the next slide. So imagine this cross-section that I'm showing in the bottom part of the figure, and we're going to take a look into the amplified version of that. So here is a cross-section of the cochlea on the left. Essentially, it's a fluid-filled structure composed of three segments. You've got scala vestibuli up on the top, which is where the stapes is transmitting its sound pressure waves. And the fluid that's in the scala vestibuli will move that sound wave along the snail-shaped cochlea. And that sound wave will go all the way to the end of the cochlea and then travel back through the bottom section, which is the scala tympani. So that's how the fluid will move the sound pressure waves into the cochlea. But the transduction happens in the center section, which is where I'm showing a little rectangle and I'm calling it organ of Corti. The right side is showing organ of Corti amplified. So there you can see, so let me just quickly go over the structures. The organ of Corti sits on this base called the basilar membrane. That's at the bottom. And that, imagine that to be extending from the base of the cochlea all the way to the tip of the cochlea. So it's about 3 centimeters long. And then up on the top, you see that hand-shaped structure called tectorial membrane. So what happens with sound when you hear something, the airwaves vibrate your tympanic membrane, the eardrum, and that sets the three middle ear bones into motion, which then presses the fluid into your scala vestibuli, and that forces the basilar membrane to go up and down. And it also forces the tectorial membrane to go left and right. And this motion then is transferred to the inner hair cells, which is what I'm showing here in the middle. There is nothing hair about it. It's called hair cell because of the stereocilia up on the top that looks a bit like tiny hairs. But that little structure, a row of those, is responsible for converting the mechanical sound pressure wave into electrochemical neural pulses. So as the stereocilia moves on the top, it opens up ion channels, and those ion channels depolarizes the cell, and that creates neural pulses, which you can see in the yellow, the auditory nerve fibers, which synapse into the hair cells that carry the neural pulses back to your brain, right? So that's sort of like my 3 minutes of tutorial on the neurobiology of physiology of human ear. I should also mention here the outer hair cells, those three layers that I'm showing on the right. So what roles do they play? Well, it turns out those outer hair cells, they look exactly like the inner hair cells, except they have some protein molecules in there which can elongate and contract in response to sound waves. So they end up actually doing a pre-amplification of the sound. Remember how I said the uh, the ear canal amplifies by 3.5 dB, and then the three middle ear bones amplify by another 27 dB. So there you had total of 30 dB of pre-amplification, and then this outer hair cells responding to the sound waves by elongating or contracting adds as much as 50 decibels of amplification. So in total, the human ear amplifies the sound coming in up to 80 decibels before your transduction mechanism kicks in and converts those sound waves into neural pulses. It's a really fascinating device. I should also mention it's not a linear amplification. Human ear is perfect in terms of its nonlinear functions. So it will amplify faint sound a lot more, and then it will amplify loud sounds less, right? So you have a very dynamic adaptive system. So let me just go forward, not get lost in biology. It should take like this part alone should take 2 graduate level classes to really dive deeper. I don't have time for that. Now let me mention something about the frequencies. So, I talked about sound pressure levels and decibels and all that. Where does the frequency selectivity happen? Well, so remember how I mentioned the basilar membrane, which basically is going up and down in response to sound waves. So the basilar membrane has a wave-like vibration pattern when it gets exposed to sound pressure waves. So different parts of the basilar membrane along its length vibrates to different frequencies. So your human ear almost behaves like a Fourier transform device, right? So if you have high frequency sound coming in, the basilar membrane, the base part of it will vibrate most. And if you have low frequency sound wave coming in, the wave is going to propagate all the way to the end of the basilar membrane. So it almost works like a nature's Fourier transform device. And this slide I'm showing here, a frequency tuning curve of a cat's auditory nerve fibers. So as you can see, different frequencies, I'm showing from 100 hertz to 50 kilohertz, right? Cats are very sensitive at higher frequencies, unlike humans. Humans are typically between 20 hertz to about 20 kilohertz, right? So you can see how as you probe different auditory nerves by inserting electrodes into individual nerve fibers, you can measure its frequency response. And you can see the nerve fibers, individual nerve fibers have very sharp frequency response. With that, I need to mention this because as we talk about hearing loss, you'll see that even though a lot of degradation in human hearing happens at the sensor level, a lot of complaints that you'll hear about speech understanding happens in the auditory cortex. My colleagues in the medical school like to say, you don't hear with your ear, right? You really hear with your brain, because ear essentially is simply converting stimulus of sound into neural pulses, which then it's sending to all the way to the auditory cortex. But along the way, if you follow those red and blue arrows, those neural pulses come out of the cochlea and they go through the brainstem to the midbrain to the thalamus and all the way to the sides of your heads, which is where the primary auditory cortex is, right? Which is where your processing for sound happens. And obviously that gets combined with your vision, motion, and a lot of other elements of the cortex to make meaning of things, right? I'm going to talk a little bit more about what happens in the auditory cortex as you get hearing loss. Just one more comment about frequency selectivity. So it not only happens in the ear, in our auditory cortex, the neurons that are dedicated to processing sound, there is frequency selectivity built into that as well. For those who have studied vision, and in vision we talk about retinotopic map, right? How from the retina itself, you have a map in the visual cortex, of the visual part of the cerebral cortex. You have a retinotopic map that's preserved from the visual field back into your visual cortex. Same thing happens in sound, except you have tonotopic map. So some of the blocks of auditory cortex responds best to specific range of sound frequencies. Here I'm showing in kilohertz. So the 0.125 all the way to 20 kilohertz. It's for macaw monkey, so it's close to human or cortex. So this is the last slide on biology. So I'm going to bring the discussion back to human speech, human hearing, decibels, and frequencies before I move off of this topic. So the x-axis is showing frequencies. As I mentioned, ideal human hearing works from 20 hertz to 20 kilohertz. But as you get older, even when you are 30, 40 years old and then get 50, 60, we tend to, the frequency range tend to shrink. So for me, probably around 100 hertz or so at a minimum, and then I'm probably sensitive to probably about 10, 12 kilohertz, no more. As you get older, the higher frequencies will degrade, and I'm going to talk about that. And then y-axis is the decibels and sound pressure levels. Remember how I talked about 0 decibel, which is 20 micropascals, right? Because it's 20 log 20 over 20, so that's 0. You see why we picked the number, because at 1 kilohertz, that's 1000 hertz, you have human audibility level is 0 decibels, right? So that's why that's used as the reference number. But here is what you should remember. If you follow the green curve down below, yes, you can hear 0 decibels at 1 kilohertz. But if that sound is at 100 hertz, low frequency, you will have to increase the loudness level almost all the way to 40 decibels for you to hear it. So we are most sensitive to between 500 hertz to about 7 or 8 kilohertz of sound. And why is that? Well, it turns out we have been evolving to understand human speech the best we can. So, the primary purpose for the auditory system was to communicate with each other. And obviously, you have, while you are perfecting the system to increase its responsivity for the human speech range, we do have some residual capabilities in the lower frequencies than human speech and higher frequencies than human speech as well. And I want to point your attention to that little light green island in the center. So that's where conversational speech happens, between about 400 hertz to about 4.5 kilohertz, and then loud about 65 decibels. That's typically the range of human conversation in terms of frequencies and sound pressure levels. Okay, so now let me move off and talk about hearing loss a little bit. So the best way to explain this is to show what is called an audiogram. So if you ever visit an audiologist or an ENT, such as my colleagues at Stanford Ear Institute, they are going to take you into a sound booth that's absolutely quiet. And they will instrument your ear with devices to play sound levels at various different loudness levels, and they will establish your audibility levels. And then they will give you a curve. They'll say, well, this is your audiogram, this is how it looks like. So I picked an audiogram of a patient with some hearing loss that I'm showing here. And this happens to be a typical shape of an age-related sensory neural hearing loss. The typical neurobiology of it is that, as we age, due to overexposure of sound and just natural degradation in our physiology, there is physical degradation of the synapse between the hair cells that I showed you that transduces sound into electrochemical neural pulses, and the auditory nerve fiber, which is responsible for taking those neural pulses and communicating it to the auditory cortex. That synapse itself degrades over time. So this person here, you can see, has relatively normal hearing, up to about 500 hertz. remember, human speech happens higher than 500 hertz, right? So if you have hearing loss between 20 decibels to 40 decibels, you are considered to have mild hearing loss. And then if you have loss bigger than that, let's say between 40 decibel to 70 decibels, what basically that means is, in order for you to barely hear that sound at a particular frequency, that sound level has to be amplified by 40 to 70 decibel before you barely hear it, compared to normal hearing person. So that's the definition of it. So moderate hearing loss is between 40 to 70 decibels. Severe hearing loss happens between 70 to 90 decibels. If you have anything beyond 90 decibels, you're considered to have profound hearing loss. Okay, so um, uh, I'm going to come back to this person that I'm showing here. You can see, I said speech happens to be between 500 hertz to about 5 kilohertz. You can see, let's look at, let's say 2 to 4 kilohertz. So between 2 to 4 kilohertz, this person has about 40 to 80 decibels of loss. Just remember that, because next chart, what is called the speech banana, because it does have a banana shape. But a couple of things are shown here, which is where, when you make sounds, when you talk, what sort of phonemes happen at what frequencies and what sound level. Pay attention to between 4,000 and 5,000 hertz. So those are the consonants, F, S, T, TH. Those happen to be high frequencies. And we are making that sound about 20 to 40 decibel levels. Now think about that. If you're making 40 decibel levels when you're saying F, thirsty, first, what will happen to this person? This person will not hear any of that, because this person has between 40 to 80 decibels of hearing loss at those frequencies, right? Not going to hear consonants. Back to the banana, the lower frequencies between 250 to a kilohertz happens to be the vowels, like A, E, O, U, the loudness levels. So if you ever hear somebody say, I can hear, but I don't understand speech, that probably means they have sensory neural hearing loss, where the lower frequencies are fine, they can hear fine. They can hear the consonants, the fricative transitions that, that separates T from a D, P from a B, right? That's what they complain. Okay, so here's what I thought I would do. Numbers are one thing, but you have to, so when I first saw this video, it's made by the Ear Science Institute in Australia, they simulated hearing loss. So this lady is going to sing a song, and it's going to simulate the effect of hearing loss by simulating multiple decibel levels to depict normal hearing, and then mild hearing loss, and then moderate hearing loss, then severe hearing loss to profound hearing loss. I'd like you to listen to this. I know I'm young, so that's normal hearing. Mild. Back to normal. For once in your life. So you get the point. Did you hear anything when it was simulated for profound hearing loss? None. So the reason I see a lot of people, part of my daily job, I meet with a lot of patients, talk to a lot of people, some famous people to not so famous people. They all come to get, they would literally cry after they get fitted with hearing aids. Because think about the life that I showed you, someone with a profound to severe hearing loss, you hear nothing. Even when you have moderate hearing loss, you're losing those consonants, so you don't understand speech, right? So when you fit somebody with a perfectly programmed hearing aid with our sound algorithms, people cry. The tears come out and they'll hug you. We're literally, that's so humbling to make such a profound impact on people's lives, I wanted to show you this quote from Helen Keller, who was both blind and deaf at the same time. And she is said to have said, blindness cuts us off of things, but deafness cuts us off of people. So, it's not pleasant to be blind or deaf, but she was asked if she could regain one sense, what it would be. And the legend has it that she said, I would rather get back the sense of hearing. The other thing I want to quickly go over that's is very well understood in the medical field, but not so much in the technical community. Just how much negative impact living with hearing loss can have. So first are the two obvious ones, dementia and isolation. Isolation, the way it happens typically, as you start to get hearing loss, you get 50, 60 years of age and you don't really hear well, you don't understand speech, you really feel like, I don't want to go to that party, I don't want to talk to them, I don't want to go there. So you tend to slowly but surely withdraw into isolation. And what happens is that accelerates the severity of dementia, even Alzheimer's. But what happens if we don't send signals up our cortex for processing? Those neurons degrade. So there is a direct correlation between living long time with untreated hearing loss and degradation of dementia and Alzheimer's, loss of memory, etc. The next one is tinnitus. I don't know if you know about this. People with hearing loss tends to have a sensation of phantom sound. I have good friends who have considered committing suicide because they have this phantom sound in their head and they can do nothing about. And it's directly related to hearing loss. If your organ is not creating the signals to feed into the auditory cortex, the cortex makes up its own, and that happens to be the phantom sound. Next, surprisingly, safety and balance. People with mild hearing loss tends to fall down 3 times more. And every 10 dB of hearing loss beyond that has 40% higher chances of falling down. And so this is really the direct correlation that shows this. So let me go forward and talk about hearing aids. So first, a very quick, fun illustration of what it used to be when popular press talks about hearing aids. Anyone knows who this gentleman is? So this is Ludwig van Beethoven. And the saying has it that he was developing severe hearing loss, and by the time he finished his life, he had to turn back to see people applaud to his performance because he couldn't hear anything. So it's amazing that he was performing and he was not hearing his own performance. I had the luxury of visiting his museum in Bonn, Germany. So this ear trumpet that you are seeing, which was his hearing aid, is still there in his museum in Bonn, Germany. And then technology progressed through the middle of 1900s, all throughout the 80s. Devices got smaller like this. So you had a box that would have all of the electronics. You would put it on your body, and a little device will basically carry the electrical signal and play sound in your ear. Fortunately, after 2000, a lot of the development that had happened in semiconductor and digital signal processing chips, and then MEMS transducers for both speakers and microphones. So those really made possible what are considered to be modern hearing aids. But that said, I have to say, when I joined this industry in the summer of 2017, hearing aids were just a single function device. So you'd buy it, actually expensive devices, can cost you anywhere from $6,000 to $8,000 a pair for good quality hearing aids. And they were doing one thing, they were only amplifying sound. So when I left Intel and joined Starkey, one of the reasons I left and joined this particular industry and not anything else, in learning about it for a couple of months, I got so convinced that we could make such a big change in hearing aids and hearing devices that it would be just phenomenal. I spent 2 months, talking to the owner and CEO of Starkey. He's, we are a privately held company. So, he's a doctor and he started this company, bootstrapped it. We didn't raise any money. and very profitable company. So I spent 2 months with him, and I got fascinated by just how much we could do. That's the story I want to tell you now and show you some things about what we've done in the last 3 years in transforming hearing aids. So first off, the design, right? So I come from Silicon Valley. You gotta make the devices look cool and not the old, ugly devices. So what I'm showing here are two kinds of devices you'll see that we made over the last couple of years. There are two kinds of devices. One is called on the left I'm showing is called the post-auricular devices. Essentially, things that go around your ear. That's two of them I'm showing on the left. And then the two on the right, we actually just introduced earlier this year. I pushed my team to see if we can make something that looks like a consumer electronic device, right? So first of all, in order to show off, so I was, holding my own guns, but these post-auricular standard devices, how small are they and how good are they? So I'll challenge Sophia. I've been talking to you for the 15 minutes before the presentation, and then half an hour into it. Did you realize that I'm actually wearing my devices?
Not
So
at all.
it's
No.
unfair because I'm on a video camera, but I can tell you when I'm in a room with somebody, I'll walk up close to them and they'll say, "Are you kidding?" Because there's nothing in there, right? So I'm going to take out the device is sitting. There's a post-auricular devices that I'm showing on the left side of the. So that's those devices, and it's designed such that all of the electronics is in this little white package. In there, we have two microphones. We have a digital signal processor chip. We have a rechargeable battery. I'll say a bit more about the battery. And then it's got a Bluetooth radio, custom-built Bluetooth radio for connecting with the phones and other devices. And this little tiny device that you see up on the top is the MEM speaker that goes into my canal and creates the sound, right? So when I put it on, you won't see it at all because that little tube that connects the electronics into the ear, it's transparent. So you can see, in fact, I have both ears. This is the right ear one. So those are the post-auricular devices. So we really made a pair of devices that I want to have even if I don't have hearing loss. I don't have any hearing loss. I use it all the time. I'll tell you why. So one of the reasons I'll tell you now, I use it as my Bluetooth headset for the sole reason that I get 24 hours of battery life from these devices. Not the standard consumer electronic device like a AirPod or the Bose device or Samsung device. You might get 3, 4, 5 hours. I put it on first thing in the morning and then I remove it when I go to sleep, put it on a charger. All day I get a phone call. I don't need to look around for any device. It's in my ear, right? So I don't have any hearing loss, but I use it for that. In the canal custom devices that I'm showing you here, we just introduced, and those are tiny devices as well. I'm holding up here. So the difference from the consumer electronic device is that they're custom made for your ear. So we actually create a 3D imaging scan of your ear canal and perfectly fit it, right? So it's just made for you. Everybody's ear has different shapes. So it's, if you order Starkey's ITC rechargeable custom, we're the only company, by the way. No one else has been able to do rechargeable custom devices that have Bluetooth radios and all that. I'm sure other companies will catch up, but so far we're the only ones. We want to remove the stigma. When you see somebody with this device, you don't know whether they're just listening to music or is it a hearing aid? Is it a Bluetooth device? You don't know anymore, right? Next. So here's where the catch comes in. Everything I showed you so far, single function. My vision was we'd like to have this in-ear device track my health. Where else the best place to do biometrics but your ear? Where does the doctor measure temperature? Or where can you measure heart rate and SpO2 better? So in-ear device. And then personal virtual assistant. I would simply like to tap my ear and ask a question, right? So those are the things we've built into this device. Let me go very quickly into the technology domains, and I'll not be able to, each of these topics probably requires an hour of discussion if you want to really learn about the detailed implementation and algorithms. I don't have time for that. So I'm going to flash through a few key technologies. First, we have been really aggressive last couple of years in adopting machine learning for sound processing. So even though the device in my ear, let's say, if I had hearing loss, the primary purpose would be to amplify sound. Well, why should we amplify every sound? So we built a very lightweight machine learning classifier that works right in the hearing aid, and it works real time. Every 6 milliseconds, we're taking a snapshot of the acoustic environment and doing a classification of determining what's going on around me. Is that a human speech? Is that a wind noise? Is that a vacuum cleaner machine noise? Am I in a car? Am I listening to music? So we have a number of classes that we can accurately classify and do signal processing accordingly and decide what sound to amplify, what not to. And then remember I said we have 2 microphones on each devices. So we can do actually really nice binaural beamforming and binaural signal processing. So that's the other reason I use these hearing aids for. In good times, when I'm in a restaurant, having a business meeting like the one we had, Sophia, for OpenCV board meeting, if I have my hearing aids on, I can discreetly go into my app and turn on the beamforming function, and I would get better signal to noise ratio for the person who's talking in front of me. Much better signal to noise ratio than my normal perfect hearing, right? And I can raise my volumes of the hearing as well, so I can hear you louder. So those are the reasons I use it in meetings as well. The next, the other thing we just introduced, we used AI to provide another function. So you can simply double tap. So we have 2 devices. So you can program it to double tap on the left or the right. So if you double tap on the left on my device, it will bring up what we call edge mode. And it will particularly enhance the speech clarity. It's particularly useful when you're surrounded by people with mask, because mask attenuates the speech high frequencies more. So if I double tap on my left ear, it's going to amplify speech signals better, right? So it's quite an amazing invention. We're getting a lot of good feedback about it. I'm going to play a little video to show you what happens when you take sound signals when somebody's talking in a loud environment. So you'll first hear speech in loud environment, pay attention to see if you can understand. And then I'm going to feed it through the machine learning and sound processing to amplify speech and cut noise. Let's see if you can appreciate the difference.
Red, and I'm just staring at it for a moment thinking, this is really strange. For a good 2 or 3 seconds, I'm seeing cars, 2, 3.
So I hope you could hear the difference in speech understandability between the first half and the second half. This is literally my team, algorithm development team, eating lunch in cafe. And so you can see how much speech clarity you can get with machine learning. And then we have built-in sensors, like no other hearing aid ever had sensors inside besides microphone. So we have built-in very tiny, low-power motion sensors to measure my steps, activity, move, like everything your Apple Watch or Fitbit can do, my hearing aids can do. So all I have to do is just, my hearing aid app is tracking what my score today is. So that's the body score. But even more important, we call it brain score, but we're measuring social engagement. So if I sit in my room all day, quiet, and don't participate in any conversation, I'll get low score. If I go about having conversations, socially engaged, I'll get a high score. Because just as taking 10,000 steps is good for your health, being socially engaged is very good for your health, particularly when you are older. We want to measure that. And because we have microphones, right, and we've got machine learning, we can classify speech. So that we're doing that. The next, again, I'm not doing justice to it, I need to go fast. We are the only hearing aid in the world that detects fall. So, we have been able to develop a classifier for fall such that if I fell, my hearing aid would automatically classify it and then send alert signal to my loved ones via the phone. And this is the part where I have to say this one thing that makes my attempt at leaving Intel and coming to this medical device industry worth it. Because just the other day, I was presenting in a forum, and one of the audiologists out of South raised hand and said, I need to share a story. Apparently, an older gentleman in Alabama were wearing up these devices, and he had fallen in his home, and he was living by himself. And his devices detected fall, sent an alert message to his son, who was in Mississippi. So his son got alerted and called his dad. But he had fallen, injured himself, and phone was not in his reach. So his son then called the local police station and sent help. And it saved that old gentleman's life. And I was told if he didn't have his hearing aids, he might have died. right? So, I get goosebumps when I hear stories like that. And false statistics, as you know, when older people fall a lot, right? So every 11 seconds, an older adult is treated in emergency for a fall. Every 19 minutes, somebody's dying from a fall in the US alone. So we want to be able to help because many of these people use hearing aids. And I just want to let you know what else we are working on right now. So, uh, very soon you'll see other physiological sensing coming out of our devices, cardiovascular sensing, temperature measurements, respiratory health, emotion measurement, etc. These are with new sensors that are built in. And then I promised I would talk about vision. So, the magic happens when two domains come together, right? Having spent many years in computer vision, there is really an opportunity to help both hearing and vision impaired people. You might be familiar with a company called Orcam in Israel. Dr. Amnon Shashua, is a good mentor and become good friends during my days at Intel when we bought Mobileye, his other company, and he's the chairman for Orcam. So we worked together to create this pairing of the hearing aids and a vision system that basically clips on on the side of your eyeglasses, and it has local processing capabilities. I want to show you a quick demo of it.
Text reading. A large rose tree stood near the entrance of the garden. The roses growing on it were white, but there were 3 garden. Face recognition. Jane. Money notes detection. $50.
So you already have it in the market now, and the possibilities are endless because you're adding more and more use cases. All you have to do is show your wrist, and it tells you what the time is. You don't need to have a watch in your wrist. So there's a lot of people that come to get help from our audiology offices, and they don't see very well. So now they can walk out with a pair of devices that help them with their vision as well as with their hearing, and it's discrete because it's communicating through Bluetooth into the device itself. And to live this, I have to say, you might say this bit of a gimmick out of Silicon Valley. But if I have the ear or in the device in the ear, it's connected to the cloud. We converted it into a virtual assistant. Remember how I said you can tap the left and it optimizes for speech? If I tap the right ear, it activates a virtual assistant, and I can ask a question, and it brings me an answer in my ear. So I could say, what's the weather? And I'll hear the answer in my ear. It translates languages with near real-time speed. So it's got about a 50 to 100 milliseconds of delay. So if you're patient, you can have a good one-on-one conversation with somebody who doesn't speak your language. So a little bragging before I end and take questions. We had a journalist out of Bloomberg come and visit, and I showed him the demos of this device. And he wrote this article, "The future of wearable technology is called a hearing aid." And he said, even if your ears are fine, you might want a device that translates languages. And at the time, we translated 27 languages, tracks fitness, and monitors vital signs. So it's no longer just a hearing aid with sound amplification. We got the Times Best Invention Award 2019. We were actually the top of the list. CES gave us the one of the innovation awards, even though it's not a consumer electronics device. And I'm proud that we received the 2020 AI Breakthrough Award because we're using AI in the domains of helping people, right? So with that, that's my contact information, Starkey email address, as well as the Stanford email address. We are extremely open and eager for collaborations. We work with universities, we work with individuals, other companies. We are a private company as well, so less sensitivity about IP and everything else. We're really, what we ask ourselves is, can we help people live better lives? And if the answer is yes, we get excited and we work together. So thank you for the opportunity, and I can take questions.
So Dr. Achin, there is a question from Ravi Krishnan that the question is about, is it prescription only, and can regular person buy it?
That's a good question. I should have mentioned already, hearing aids are medically regulated class 2 products, medical devices. So you can't buy it over the counter or by yourself. You do have to go visit a professional. So you have to see an audiologist or an ENT. They're certified to test your hearing and fit you with hearing aids. Why is that, right? You might ask. Well, it turns out this innocent looking device, if you're not careful with it, you can create a lot of damage, because let's say you have normal hearing, but you create 100 dB of sound in your ear, you might end up creating speech-induced hearing loss. So the regulatory bodies control who can test and program the hearing aid to fit your audiogram, so that you can have a good experience and not damage yourself. So it is a medically regulated product. You need to see an audiologist to get it.
I think also Chris Yanchi, our co-organizer. Chris, did you have any questions for Dr. Achin?
Yes, thank you so much for speaking to us. This has been really, really nice. I was curious. So you mentioned that there were 17 million devices and about 466 million people affected. And at that slide, you had said that a large portion of that is due to the social stigma of using the device. I find that very easy to believe. That makes perfect sense. But I would be interested to hear your thoughts on, do you think any of that is related to accessibility? Like, is there some barrier in the cost of the device, since as it affects the older population in a way, right?
Yes, no, it is but all of those factors weigh in.
Yeah.
Stigma certainly, as you said, but with the new devices that are starting to come out, the ones that I'm showing you, they'll hopefully remove stigma being the primary reason. Because it looks like you see so many people in the plane and around you with AirPods or other devices. They're playing a strong role in removing stigma of in-ear devices. So that hopefully that doesn't continue to be the case. Accessibility is an issue. You do have to go to an audiologist. You can come to a Starkey audiology office, or you can go to Stanford Ear Institute, or many number of audiology offices, but we do have to see an audiologist or an ENT who's a medical professional in order to get these devices. There are a lot of devices you can buy online, but those are called PSAPs, like personal sound amplification products, not nearly as good in terms of fitting somebody well. And then the other part is the cost you mentioned. Certainly, when you have to go through a medical professional, the price you pay, vast majority of that goes actually into the fee for the professional. The device part of it is relatively small percentage, the cost of the device itself. So now that said, my colleagues here in the medical community quickly point out, in Europe, it's UK, hearing aids are covered by the government insurance. So you can get it for free. You can just go and get it for free. Even there, the penetration of hearing aids is 40%. So, it's not just you make it cheaper and everybody will get it. The people say phones used to be free or $50 or $100. iPhone costs $1,500 and I run to buy one, right? So price may not be that one. But suddenly there is a bill that's got approved in US Congress, and it's still being debated and finalized. It's not approved and published yet. It will allow for a category of hearing aids with lower levels of gain to be sold directly to the consumer or over the counter. We hope that might increase the accessibility and more people will buy it. I think that what we're seeing, by the way, that 17 million was number of devices sold in 1 year. So,
okay.
Right?
Sorry, my misunderstanding.
Right. So every year we are starting to see more and more devices being sold. I do think we're on the cusp of a big breakthrough with all of these factors playing in: good devices, better experience, better accessibility, multifunction. I'd like to have my health monitored, right? I'd like a device that will tell me if something will happen to me before it happens. So we think with all of these added functionalities, I believe we'll see more devices adopted. Good question. Thank you.
Achin, this is Santosh. Hope you can hear me okay.
Yeah, we can hear you.
Yes. So just a quick background. Since I work in BCIs, brain-computing interfaces and fMRI devices, so I do have two questions, if you don't mind. So first being on, of course, Starkey being a private company, I'm guessing you don't have any process where you can actually, give the data for open source. I was just kind of curious to know. I'll tell you why. Because I've actually supported, Air Force, where the number one claim for U.S. Air Force is in the name claim for workplace hazard is actually based on the hearing loss,
Mhm.
right? So it also, we have actually explored a lot of genome data, as to who are susceptible for hearing loss versus
Right.
some are not actually. One of the genes
Mhm.
is actually ACTG1. I'm just naming that because I worked extensively on that, right? So I was kind of curious, if you have any guidance on exploring the data from these hearing aids, and then at least building a correlation as to who is more susceptible to, hearing loss.
Right.
So that's the number one question. So I'll let you actually answer that, and
Sure.
I'll actually go for the
Okay.
next.
It is I think we should, I'll give you a quick answer and then we should follow up with a bigger discussion. It's an extremely
yeah.
important area because as we started to dive in 3 years ago into machine learning, it's all about the data and there's a lot of new things we're discovering.
Yeah.
And by joining hands with genomic studies, which we do not do ourselves,
Yeah.
but we have a lot of other data, behavioral data, hearing loss data, usage data, we can correlate them really well.
Yes.
And you're totally right that I should have mentioned, sensory neural hearing loss, we are genetically disposed. Some people have higher chances. That said, the sound-induced losses are brutal. It doesn't matter whether we have strong genes for hearing or not.
Right,
If you
right.
expose yourself to loud noise, you're going to get hearing loss. Which is why Veterans Affairs happen to be one of our largest customers.
Yeah.
I should mention something else since you brought it up. It was fresh off the press. We just introduced 2 weeks ago a device that we call Sound Gear, and I'll be happy to share details with you. It's a sound protection device.
Okay.
So it's got all of the components that I showed you of the hearing aid, all of the functions, but it can provide you 25 decibels of noise reduction.
Oh,
Right. So not just, so this is opposite of hearing. You can amplify, but it can also cut.
right.
So it's designed for people who are exposed to loud sounds, including hunters, right? So it can quickly detect transient loud sound and cut it off.
Right,
So you
right.
can participate in conversations, but
Yes.
you know for sure you have protection if there'll be a loud sound will cut off, right?
Nice.
So we just introduced, this is not a medically regulated product, by the way.
Gotcha.
We should talk more about this, might be helpful for your Air Force
No,
buddies.
absolutely. No, I will definitely connect with you on LinkedIn. We should definitely connect. So second thing is, interestingly, you didn't mention about emotions, right? Sentiment analysis.
Right, I did, yeah.
To me, based on the EEG background, I feel confident in actually assessing the alpha levels or the theta levels.
Right.
Are you implying that, there could be some elements of an EEG in your device at all?
Yeah.
Any kind of thoughts on that?
Yeah. So a couple of things. One is we can actually measure sentiment in other ways.
Okay.
It's like if you are, let's say, if you walk into a place, you can feel whether it's joyous environment or is it sad environment. So you can use machine learning on acoustics to try and find that with fair degree of accuracy these days. But on EEG, we have research projects. It's all about if you allow for a cap, certainly. But if it's in ear, there's not enough special differentiation between the reference electrode and the signal electrode to get meaningful signals out of it yet. Right. We are researching it. We've got really interesting studies going on. Not just us. This is going around the world.
Yes.
Can you get meaningful EEG signals from ear around the ear? It's being studied.
No, that's good. Thanks. I'll definitely connect with you. Thank you.
Thank you.
So one question related to the accessibility and affordability, right? So you were mentioning that a lot of it is driven by kind of the cost of getting it diagnosed. So have you guys looked at machine learning for the diagnostic space, because my background is in signal processing, and I'm interested in the accessibility piece of this. So, obviously I see all this, kind of innovations in the device space, but I feel there's a huge potential, especially once you have this database, to use that for accessibility as well, wherein you can use machine learning to, maybe you can ship something to a person, he or she can try it out and figure out, what is the tuning needed, right? So what are you getting in that space?
So I should clarify, it's not difficult to measure hearing loss. In fact, very beginning of the presentation, I showed a free Starkey app you can download from Apple App Store, Google Play Store, and you can check your hearing. So it's not difficult, because what is hearing loss but playing sound at different frequencies and then asking you what was barely audible for you, right? So it's fairly easy to do. But the reason why FDA still requires you to go to an audiologist or ENT is the same reason why you go to your doctor for things that are relatively straightforward to fix, because there's a lot of, it's a medical condition. So an audiologist will simply not, she's not just putting things in your ear, measuring and letting you go. She's actually having conversations with you to understand what, very sophisticated ways to figure out where your problem is. Is it in the, is it in the outer, in the middle ear? Is it the ossicle chains, those 3 middle ear bones that lost its effectiveness, which will be characterized to be mechanical loss? Or is it sensory neural loss, where degradation happens between the synapse between the hair cells and nerve fiber? Or maybe your audibility is fine, but maybe you need rehabilitation of your auditory cortex for understanding speech, because your degradation happens to be somewhere else. So this is not a straight. There is a reason why people take 4 years of medical degrees and become a doctor of audiology. I have developed respect for them because I'm a faculty member at Stanford Medical as well. So it's not just the technology part, we can do that. But when a 60, 70, 80-year-old gentleman or lady has hearing loss, and the repeat visits they have to do with an audiologist to get fine-tuned and get coached and handheld over months and even years, that's what you're paying for, right?
No, I understand that. No, I understand. What I was trying to figure out was, especially with, kind of techniques like machine learning, where you can really kind of analyze a much higher dimensional space, right? So obviously the frequency domain, traditional audiogram is one piece. You could try, you could have data based on different types of speeches being fed to the person. And I'm not saying that,
no, those are done. Those are perceptual testing. Yes.
Okay, those are all done, right? So trying to see whether these techniques can be used to make it more accessible, right?
Right.
So
I'd love for you to try out that free app I talked about and give some feedback.
Will do.
And obviously, it's like a normal. You want to, besides understanding audibility at different frequencies, you want to what really matters is, are you understanding the content in the speech, right? And those are taken into account in deciding what algorithm will best help you.
I'll check it out. How do you calibrate the levels?
So that's programmable. So we got a DSP in there. So the way the device architecture works is got 2 microphones for beamforming, the sounds converted into electrical signals with a MEMS transducer, fed into it goes through an A to D, and then through a digital signal processor that does all of the machine learning plus signal processing. And then the output is converted into digital domain with a with A to D, D2A, sorry, analog domain. And then that's fed into a MEMS transducer for converting back into sound. So you have 24 channels of frequency bands that goes on into the signal processing. So we have very fine-grained control of how we make the adjustments. But we do that not just mechanically fit your audiogram and that's it. We take into account machine learning of sound levels, your perceptual limitations, and your feedback in deciding what's the right compensation scheme for your individual hearing loss.
Got it.
Great, Dr. Achin. There's another question from Ravi Krishnan. And Ravi, you can ask yourself the question, or I can, let me do it for you right now, so we could fast forward to other questions, since there is a big queue of questions here. So
yeah, I think he just answered my question. I was asking about the.
Okay, so he did. And how are you able to run all this on such tiny device, right? Ravi, that was your question, right?
That's a perfect question. I hope somebody will ask it, because when I was at Intel, we were dealing with, 10 watts, 20 watts of low power. And then the first computer vision chip we started shipping out of Intel had less than 1 watt of power consumption. We were so proud. So now I tell you, now we're in milliwatts. So, this sort of devices, in order to provide all day battery life that you need to, because it's not a consumer electronics device, patient using hearing aids is really relying on the device for all day operation. So I got milliwatts of power budget. So that's where most of the engineering work goes on, in fine tuning the machine learning models to make it extremely power sipping. Not just that, even Bluetooth connectivity. So I'll tell you, when you use an AirPod and connect with iPhone, you might be consuming 20 milliwatts of power, maybe 15 milliwatts. But we can stream audio with less than a milliwatt power consumption. So we do extreme amount of optimization in power in order to run the device.
That's great. Another question from Arthur Zinger, our member from Palo Alto. He's asking, many sensations are translated by association from one sensor to another. Can you use this to translate hearing? And Arthur, please feel free to unmute and ask if you want to. But Dr.
You've
Achin,
asked it clearly.
okay.
Women translate beauty to perfume all the time, and we silly men are affected by it. Like in an analogous way, can you translate hearing to some other sensations?
Right. Well, so there is a rich study of research about this on the interplay or interconnectivity between different perceptual systems. Smell is a strong one that you bring up, but between even visual and auditory, there are good examples. One you might want to look up is a very famous experiment that was done decades ago by Professor McGurk, and it's called McGurk effect. I'd like you to watch that video, because send me an email if you have difficulty finding it. It establishes the interplay between visual and auditory system. In fact, McGurk effect shows how the auditory system is overruled by vision. And then there are other examples where vision system is enhanced and overpowered by the auditory system. Lip reading is an example, right? So even unconsciously, we are always correcting our perception of hearing by getting some inputs from the movements of the lips. And that's why when you are surrounded by people with masks, especially patients with hearing loss, are complaining that their ability to understand speech has gone down just because they're not looking at the lips. So that's another example of vision helping audition. And we are obviously trying to use machine learning to compensate for those that it double tap and then it enhances the speech signals. So those are examples where different perceptual components play off each other.
Dr. Achin, Adam Finkel has a question. He was asking how your device could be not used for evil. And another question that he was asking if it's similar to peltors that special forces use in their headphones. And he says they go for $1,500 per one. And so basically I guess he wants to know the difference, and if this could be used for evil or for good. I truly believe it's for good.
Well, so I need to give an example of my colleague's son, who is in middle school, was caught streaming music from his phone into his hearing aid when he was sitting in the class. So, that's interesting, because if you don't know I am wearing a device, you don't know if I'm streaming music. So I might be sitting in a lecture, but really all I'm doing is listening to music, right? Not really an example of an evil, but do we really know what people sitting in US Congress are doing? Are they really participating in debates, or are they? But that said, I should mention, besides the hearing aids, we also provide some accessory devices that go with it. One of them is this, if you can see it, it's a clip-on device. It's a remote microphone. So, the idea is, if I have hearing loss, I'm at home with my wife, she could have this clipped on, and then she could be walking around at home. Her voice is going to be streamed while listening to my hearing aid. So I could hear her wherever I am, right? But you can imagine doing some spying with it. I can put it maybe on my my son's study desk, and I can be on the other room and see what he's really talking about. And then, but I should also show this device here. That's a device with arrayed microphones. We actually collaborated with a company in Israel to make this. And this has a very powerful directionality. So you could put it in front of you on the table, and it can automatically beamform from the talker, the speaker, or you could manually set it. So you could be imagining all these things. I was giving an interview to a Silicon Valley conference, TechCrunch, and the reporter got so fascinated by the remote microphone that he said, "Can I try it?" So you'd have somebody go into the crowd, and you're somewhere else in a conference, and you could still hear the other person talk because this is streaming into your hearing aids. Yeah, you could have what you might consider superhuman hearing capability.
Yes, and I'm going to ask the last question since we are kind of out of time. So, Dr. Achin, how did you leave position of vice president at Intel Corporation to go to a privately held medical device company? How did that happen for you?
Thank you very much.
Impressive
So
transition.
I was a happy camper at Intel. No complaints. It's a great company. I learned a whole lot. Early on when I joined in 2000, I had the luxury of interacting with Andy Grove, the legendary Andy Grove. I was very lucky. And then over time, I am somebody who got shaped by my work and experience at Intel. I also had the good fortune of starting the perceptual computing group, creating Intel RealSense, depth cameras. Now, of course, you have depth cameras in phones, but I had the privilege of being the first ones to lead miniaturization, among many other contributors. I know some of the attendees that on this talk, they had their contributions on depth cameras as well. So there was nothing bad about Intel, which is why I left. It's more about what I wanted to do with the second phase of my life. I didn't want to spend all my life at one place. And it was what it did at the end was the desire to make a contribution in the field of medicine and health, right? So I as a technologist, felt there is a big gap in adoption of advanced technology in the medical field compared to the consumer electronics world. And I felt I could make a big contribution here. And I did take the time to learn about this and see really what opportunities exist. Extremely happy about, like I was giving an example of, seeing people cry who use your technologies. So, nobody in the consumer electronics world was crying with those autonomous robots I made or my contributions to the autonomous cars. They were not crying. So I went from helping machines sense and understand the world better to helping humans sense and understand the world better. And I feel a lot, compelled to continue and, really good. Thank you for asking that question, though.
Thank you so much, Dr. Achin. I would also like to thank Chris Yanchi, my co-organizer. He's here in California, in Northern California. Of course, you, Dr. Achin, is in Minnesota right now, so thank you so much. It's 3 hours, ahead of us, and you staying up late to talk to our members and, enlighten us about the hearing aid technologies. Also, Santosh here is in Washington, D.C. area. He runs his own large meetup. Thank you so much for calling in, and definitely we should chat about how meetups could collaborate, and just great to see you joining us tonight. And definitely have to come for a follow-up talk. And the topic is infinitely interesting to everyone. And you've got some customers tonight. I think all of us will need hearing aid very soon. So.
Thank you very much. It was a pleasure talking to everybody. Great questions. I look forward to continuing our conversation. I look forward to coming back for continuing this. Thank you.
Thank you, Dr. Achin. Have a wonderful night. Bye, everyone.
Bye-bye.